All right, so we have three things we're going to write. First, to be differentiable. To be differentiable at a point A. To be differentiable at a point A means that f prime of A exists. So if you're differentiable at a point, that means the derivative at the point exists. To be differentiable on AB, to be differentiable on AB, written like that, means that the function is differentiable on, at every number. In the interval from A to B. So if you say that a function is differentiable at a point, that means you can find the derivative at that single point. If you say the function is differentiable on an interval, then you're saying that every single point on that interval there is a derivative, or there's an instantaneous rate of change. That's what that means. All right, and then last, differentiability. Nope, doesn't include the ends, just the numbers in between. Differentiability comes from the limit definition. So when we look at if something is differentiable or not, we'll look at like limits to describe it. So you'll notice that some of the information, it will be kind of like a flashback to last unit, and that's because derivatives are defined using limits. So it would make sense that the limits would give us some sort of indication of what is not going to work. Okay. All right, there are three main ways to not be differentiable. There are three ways to not be differentiable. One is to see a sharp corner or a sharp point, or they call this a cusp. And the reason that these are not differentiable is because if we talk about the left-hand limit, if we have a sharp corner, actually if you look at your pink sheet, you can see an example of that. So that's the first two. We have a sharp corner, or we have a cusp. A cusp is kind of like a corner, but it's like it curved to come together to make the little point. The reason that the derivative doesn't exist there is because the left-hand limit is the left-hand slope. The right-hand limit is the right-hand slope. So if you have a negative slope on one side and a positive slope on the other side, then those are not the same number, and we would say the left-hand limit and the right-hand limit do not agree. We're just not talking about y coordinates this time. This time we're talking about slopes. So the left-hand slope and the right-hand slope are not the same. Does that make sense? So a cusp or a corner is because the left and the right-hand limit do not agree, and we're talking about that as in terms of slope. So I'm just going to say left and right hand don't agree. The second reason we could not be differentiable is because there's a discontinuity at that point. So there's an asymptote there, or there's a jump there, or there's a hole there. So this time the limit is not going to exist at a hole when we're talking about derivatives, because a hole in the graph is not going to have a slope because it's not there, it's blank. Okay, so this time they're not going to have, yeah, they don't have a derivative, no derivative at a hole, because it's not continuous. But the limit was saying what is the y coordinate that should be there. And so that was saying like we're approaching it, but it's not quite there. But here we're going to say there's not an actual slope at that point. All right, the third way is if you have a vertical tangent line. So what do I mean when I say vertical tangent line? Yeah, the cube root graph. But what do I mean by the words vertical tangent line? Yeah. Yeah, so a tangent line is a line that comes alongside the curve, right? And a vertical tangent line would mean that line goes straight up and down. And what's the slope of a line that goes straight up and down? It's not zero. It's undefined, which is why the derivative is not going to exist there, because the slope doesn't exist. Does that make sense? Mm-hmm, exactly right. All right, so we're going to... So the limit doesn't exist because it's unbound. All right, so when we start to discuss why something is or is not differentiable, the most interesting cases are going to be piecewise functions because they have a lot going on. Okay, so we will typically look at piecewise functions because we have to check the different slopes and things like that. So here's an example. We're going to find f prime of x for f of x equals the absolute value of x. So what do we have to do first? Make it a piecewise. So I'm going to say f of x equals, and how do I write it as a piecewise function? So I've got negative x and I've got positive x. If x is less than 0, positive x. If x is greater than 0. Can you equal 0? Yeah, you can. One of these can equal 0 because we don't have a hole at the vertex, right? They actually connect. Okay. It doesn't matter. Either one of them would work. Okay. So if we go through and we find the derivative of this, it's in Mrs. Fitzpatrick's room. She said, I can't get it right now, so you're gonna have to do it tomorrow. Okay. Okay. Thank you.
Are you allowed to say greater equal and lesser equal to both of them?
No, because then it wouldn't be a function. Well, functions have to pass the vertical line test, so you have to know exactly where you're plugging it in. You can't plug it in two different things.
Wouldn't it still pass the vertical line test? Because
technically no, because you would have graphed that point twice on top of itself. All right, so we're going to go ahead and find the limit. So we're going to say the limit as h goes to 0, and I'm going to plug x plus h in this one first. So I'm going to say that's negative x plus h minus negative x divided by h. So there's my first one. That's the negative version. And I'll go ahead and I'll do the positive version as well. The limit as h goes to 0 of x plus h minus x divided by h. We're going to go ahead and show all our work anyway. So we have negative x minus h plus x. You guys are keeping all your limit notation, right? This time. So for this one, the x's cancel, so we just get h over h. What happens over here? Okay, and then what do I get? -1, what do I get over here? Okay, so I'm going to say f prime of x equals -1 if x is less than, I'm going to say less than 0. You'll see why in a second. +1 if x is greater than 0. So we found the derivative of the left side and the right side. The part that we're concerned about is what the limit is, or what the derivative is at 0 exactly, right? So what do you notice? This is our left-hand limit, basically, our left-hand slope and our right-hand slope. What do we notice about the two different slopes on the left side and the right side? They don't agree with each other, and so we're going to say that this is not differentiable at x equals 0, which is why I went from having the equal sign up here to not having an equal sign down here. So we can say it's differentiable anything to the left of 0, and it's differentiable for anything to the right of 0, but it is not differentiable at 0 because the left slope and the right slope do not agree with each other. There's a sharp corner there, okay? So I'm going to go ahead and write this. Not differentiable at 0. Because the left and the right slope do not agree. So what you could be writing is you could say f prime of 0 from the left does not equal f prime of 0 from the right. Does that make sense? So f prime of 0 from the left does not equal f prime of 0 from the right. And so that means that f prime of 0 is not defined. We don't have anything for that. Okay? You would put it on the inside because you're not going to say, this would be like saying I'm looking at the slope from the left, which would be kind of weird. You wouldn't really do that. If you put it on the outside, yeah. But you're really looking at 0 from the left and 0 from the right and asking what the slope is at those values. Well, I'm pretty sure you would. Yeah. All right, example 2. You're going to go ahead and sketch this graph. So we have a hole somewhere down here. It doesn't matter what value it is. I didn't label that. You can go ahead and say that this is going up like this. And then we have a point at 0 and a point at 2. And they kind of swoop up and connect. And then we have a point at 4. All right. So if you look at the picture, where would there be a vertical tangent? Not at 0. 0's right here. There would be a vertical tangent at 2. Yep. Yep. So vertical tangent is at the point 2, 0. Where are there horizontal tangents? There's 2 of them. Yeah, we have at 1, I could say this is 1, -1. And 3, 1. I'm just going to call those 1 because I didn't label it. All right, so we're going to say for what values of x on the interval from -2 to 4 is f not differentiable? So let's go ahead and label this as f of x. Okay, so for what values is the function not differentiable and why? So at x equals 0, why is it not differentiable at x equals 0? There's a jump, which is a type of discontinuity. And then where else? X equals 2 because there's a vertical tangent. And we know that that's a perfectly vertical line, which means the slope is undefined anyway. You're going to see in the next example. All right, so for this one, we're going to consider f of x equals cube root of x. So we're going to ask ourselves, is f of 0 defined? Is f of 0, or is the graph continuous at f of 0? And is it differentiable at f of 0? All right, what does half of the cube root of x look like? Yeah, it's an S-curve one, but it's on its side. Yeah. So it goes, let me remember, yes. It goes like this. That's what a cube root graph looks like. All right, so is it defined? Yeah. What is f of 0? 0. Okay. Is it continuous? Yes. Okay, so let's go through the definition of continuity. So part 1 is what? 3 different parts to the definition of continuity, right? So f of 0 is 0. The limit as x goes to 0 from the left equals the limit as x goes to 0 from the right. And what is that limit? It is 0, so we're going to say the limit as x goes to 0 of f of x is 0. And then what's the third part say? That the evaluation you got and the limit you got are the same thing, which they are. So it is continuous, but I should see lots of writing, right? Because you're writing it down right now. So it's defined, it's continuous. Is it differentiable? No. Why is it not differentiable? Vertical tangent line. All right, I'm not going to make you use the limit definition of a derivative to find the derivative. I'm going to give you the derivative, though, so that you can use it. We're going to learn shortcuts for derivatives in a little bit, not today, but later. And once we learn them, I'll show you guys how to find this derivative. So the derivative, if the original function is f of x equals cube root x, then its derivative is 1 over 3 times the cube root of x squared. And so if you look at the definition, or if you look at the actual derivative, the equation of it, can you tell that it's not differentiable at 0? Yeah, because if you tried to plug 0 in, you'd get 1 divided by 0, which is undefined. And that kind of fits, because if you're like, oh, I got an undefined slope there, then the vertical tangent is also an undefined slope. So that's logical, right? Okay. So we say the derivative doesn't exist there, it's a vertical tangent line. Okay. All right. I got some more notes for you. I know you're loving it. Oh. We might cut it down. Don't stress. Don't stress. All right. Yeah. Don't stress it. We'll do what we can. All right. Theorem. This is a theorem. Hey guys, we're doing notes. All right. If a function, these are the same notes. I just started another page. If a function f of x is differentiable, do we all have the same size handwriting? Okay. Okay. If, yeah, and Toby's got like 15 pages by now. Okay. If a function f of x is differentiable at x equals a, then f of x is continuous at x equals a. And this kind of makes sense because you're not differentiable at a discontinuity. So if you say it's differentiable, it must not be a discontinuity. And so then it has to be continuous. Yeah, it is very useful. This, I would highlight it, something, put a star next to it. It seems like common sense, but some students, it's like later on, they'll be looking at a function and they'll know it's differentiable and they'll need to know if it's continuous and they forget. So if a function is differentiable, it is definitely continuous. Okay, that's something that's big. Yeah. Has to be continuous to be differentiable. Just because it's continuous doesn't mean it's differentiable though. Okay, not necessarily. All right, the contrapositive of this is if f of x is not continuous at x equals a, then f of x is not differentiable. But it's a theorem. Yeah. I'd have to look up the definition. That's like the mathy word for the opposite of this, or the reverse.
Yeah, just like the thing that follows if you flip the whole thing.
Right.
It's opposite direction,
Yeah.
which is definitely still true. It's like intellectually like myself.
Okay, I'm gonna go ahead and leave it there. Yeah, so if you look at this, this pink sheet is going to go with, are you listening? Remember we talked about my students last year suggesting that you have like a little mini binder, like a 1/4 inch binder or a 1/2 inch binder, and that in your mini binder you should keep your cheat sheets, Unit 1 cheat sheet, Unit 2, Unit whatever, because when we get to Unit 5, you can use your Unit 1, Unit 2, Unit 3, Unit 4, Unit 5 cheat sheets. This is a resource page, and this would go with the cheat sheets. So when you can use this on a test for the last 10 minutes or 15 minutes or whatever. So when you get to the Unit 2 test, you're going to have the Unit 1 cheat sheet, the Unit 2 cheat sheet, you're going to have a pink sheet. We're also going to get another one, a yellow sheet. Eventually we're going to have a green sheet. You're going to have multiple pages of like resource sheets. And that's why they were saying it would be good to have a little binder so that you just have that. This is like my test taking binder. Does that make sense? Okay. So it's not necessarily super important that you get it right away, but we're getting to the point where we're starting to have more and more sheets that are going to go in there. And so it would be good to have something. It doesn't have to be a binder. It could be a folder, just something. The reason they suggested a binder, they also suggested that you put your cheat sheets in a sheet protector because you're going to handle them a lot throughout the year. So if you wrote it in pencil, it's going to get very smudgy. Does that make sense? Okay, so keep this pink sheet in a safe place. It seems rather intuitive right now, but when I start to fill your brain with more things, it's going to get to where you just forget the stuff that's on here. So it's good in a moment where you have a brain fart to be able to look back and see it and go like, oh yeah, those are the cases where it doesn't exist. Okay? All right, so keep that safe. Go ahead and we're going to work on the Larson pages. I printed those out for you, so let me hand them out.